Hello everyone and welcome. We are starting another IDEA StatiCa webinar. Today's topic is how to design and code check a pile cap. My name is oh, sorry. My name is Petra Topinkova. I am product engineer for IDEA StatiCa, and with me there is Lukas Juricek, also product engineer and specialist for concrete topics. He will show you the main part of the webinar. We are streaming through GoToWebinar platform. If it's your first time, just notice that you are all muted by default, but you can ask questions through the bar on the side of your screen. So feel free to ask anything. We will try to answer you during the webinar or afterwards if there is too many questions. Let's see today's agenda. First, Lucas will explain you some theory related to the topic. Then he will tell you some assumptions and principle of the method behind the IDEA StatiCa Detail, and then the main part, two examples. He will show you the workflow from the creating of the model, how to apply the load and insert the reinforcement, and how to read the results. Before we will jump to the main part of the webinar, I would like you to answer me a simple question. It will help us to choose another topic for the next webinars and for the other content. You should see the question right now. How often do you design a pile cap? You can pick one answer: every week, every month, many times till the year, never. So you will have just few seconds and then I will show the results with you. Last 5 seconds, then I'm closing the pool. 3, 2, 1. And let's see how it went. So most of you designed the pile many times till the year. So we can see we pick really common topic. We are happy about it. Big part of you never designed the pile cap before, so maybe you will learn something new and you can start afterwards. Okay, now it's Lucas' turn. You can start with the rest. Thank you.
Okay, Betty, thank you for the word. Welcome on the webinar. I will take a presenter. I hope you will see my screen and my presentation. So let's go on to the theory at first. I would like to start a little bit retrospectively. What are some parts on these structures, how we can split a structure. Generally, you can see this simple frame, and there are B and the D regions. Generally, B regions, these are regions where the bernoulli-navier hypophysis is valid, and there is the linear plane of the strain. Today topic will be dedicated to the D regions. These are the grained ones, where this hypophysis is not valid, and you ought to use a different approach for the analysis. So it will be dedicated to the D regions, today's topic. Some brief theory behind the pile caps, how it works, what you should consider. How I mentioned, you should use a different approach than the standard beam theory behind. Maybe you're very well known and familiar with Strut&Tie method, which is behind, which can be used for design and decode check of the pile caps. A lot of engineers are using these methods because it's very simple, but it's suffering so many simplifications which you should consider. Or right now we'll be talking about the CSFM method, It's a compatible stress field method. It's a numerical method which is behind the calculation in the application IDEA StatiCa Detail, which will be presented today. And there are some remarks what you should consider during the analysis. Generally, the shear deformation should be considered on the member or in the element. So we are using a plane stress form or plane stress task and wall elements. So this effect is considered there. And in the bottom part of the screen, you can see that if the ratio between the length and the height of the pile cap or the beam is lesser than 2, so the plane of strain is starting to be highly nonlinear, and this is very important to understand that, and you should use this this analysis which we will be present today. So this is something to the theory which is behind. But at first, before you start every software on the world, you should read out or know some assumptions of the analysis. Generally, we are using a plane stress model for design, for analysis. So you're getting the forces in a plane. Out of plane forces are neglected. The concrete in the tangent is also neglected, but it's adjusted by a tangent stiffening on the rebars, where we consider some coacting between the concrete cracks. And also, if there are a big transverse strain, so the concrete under compression is softened. So we are considering a compression softening on the concrete based on the transverse tensile strain. The element between the reinforcement rebars and the concrete, it's called bond elements, which transferring the shear force from the rebars to the concrete and ensure the deformation. So these are some very basic assumptions. If you would like to know more, we have on the page theoretical background where is everything fully explained. So do not hesitate to jump to our webpage and see what is there. So right now, I would like to at first go through the presentation. Where are some highlights which we will be doing in the modeling. And we will start with the pile cap with a steel column. So there will be two topics. The first one, how I mentioned, is a pile cap with a steel column, and some brief information about the model behind. The concrete which will be used for this pile cap is C30/37 reinforcement rebars, which will be used for design will be B500B. It's a standard reinforcement with the class of the B deductility. The section, the steel section, is HEB 1000, and the anchors which been used for the analysis are M45 with a grade 10.9. So these are some assumptions, some inputs for the analysis, and we can jump in to the first part, and this is the equivalent section for piles. Generally, you can see that the piles has a circular section. If we will be modeling that like a rectangle, so we need to like create this equivalent section. The equivalent section is based on the derivation from the area. So here is the equation which can be used for this derivation and using for the finding out the dimensions of the equivalent square section. Right now, generally, how I mentioned, we are using a plane stress. It means all has to be in the one plane. But in these connections, there are let's say 8 anchors. We are considering the anchors which are in the tension. Everything what is in the compression is transferred over the concrete. So what is very important, there are 2 anchors, and if you would like to put it to the detail and do the analysis there, and so we have to create some equivalent anchor, and the equivalent anchor is based on the equality of the stresses. So generally you have a forces in the anchor, you have also the diameter, so you have the area. From the area and the force, you can calculate the stresses, and the stress has to be same for the one equivalent anchor. So my equivalent diameter is a 58 millimeters. As you can see, the diameter 58, and we consider that the anchors will be tied up with the rebars, so we can use the perfect bond at the end of the rebar. Yeah, so it means that it's like tied up with the reinforcement rebars. These are some assumptions which are used for the analysis. Yeah, this is for the equivalent diameter of the anchor, and right now is the time how we will be putting there the loads. So there are more options how to put the loads um, from the steel column or from the anchoring. So at first, you need to guarantee that the equilibrium must be reached. Okay, so it's very important, and I would like to show you the first option where you can use the application IDEA StatiCa connection to get the forces from in the anchor, and also the concrete stress or the load from the concrete. So let me jump in. Let me jump into the application IDEA StatiCa connection, where I have, let's say, prepared this model. So you can see this is the anchoring, and we need to receive the forces in the anchors and also the forces under compression in the concrete. So I have, here is my combination, ultimate limit state combination, you can see here, and if I will check it, I can get very quickly the equivalent stress and mainly the bolt forces. Yeah, the bolt forces are here. So you will get these 2 forces, create this equivalent diameter of the anchor, and put it to the application IDEA StatiCa Detail immediately. Here are also the force. So this is what is under tension. I can show you the deformation, so it's better to see that. Yeah, you can see how it's bended, and here has to be some compression. So you will just jump into the stress in the concrete, and here you can see how it looks in the concrete. Here is the tab for concrete block, where you can find some average stress which is calculated based on the stresses and on the force. Here is the calculation. You have a force, you have an effective area, which is here, and you will get this average stress. So this is the first option how you can put the load to the application IDEA StatiCa Detail. The second option is to use the hand calculation, get the equilibrium, and or you can use also our other application from the family of the applications of IDEA StatiCa. It's called IDEA StatiCa RCS. It's for reinforced concrete section design, and I would like to also show you that you can put here the ultimate limit state combination, characteristic combination, quasi-permanent combination, and you will get the response. So it means you will get the forces in the anchor, and you will get also the stress which is in the compressed area of the concrete, and from the stress you can derive this load, which will be applied to IDEA StatiCa Detail. Yeah. So this is option which I've preferred right now for putting the forces, and this is how it will be looking after we will jump to the application IDEA StatiCa Detail. And let me to move on to the topology optimization. In the topology optimization, from that analysis, you can see some tensile areas and the compression field, and it tells you how the structure behaves. So generally, these are some principal stresses, linear principal stresses. Yeah, this is the linear analysis. So it will tell you that you can consider some tensile forces in the piles. So you should put some reinforcement, because from the assumptions the concrete in the tension is neglected. And we will move on to the interpretation of the results, but I will let it to the application. So let's go on. I will at first open IDEA StatiCa and jump through concrete. And here is my application, IDEA StatiCa Detail. So it's been pop out here, and we can create a new project. In the new project, you can do the design according to Eurocode or the ACI. Generally, we will be preferring today Eurocode code check, the concrete grade C30/37, reinforcement grade B500B, and the concrete cover 60 millimeters, because we are in the pile caps, so there has to be the higher concrete cover. We also like created for you some predefined templates. These are some discontinuity regions which are frequently used, but we will be starting with the general input at first to show you how you can do that very quickly by this option. So here, using this plus button, you will select some subregion or detail. Generally, you can see here are the many, but we will use the wall. The wall, here is some property grid where you can specify the width, which is 3 meters, height is 1 meter, and the thickness is 0.8 meter. The concrete grade is here. If you switch it to the 3D rendering, you will see that you will get this shape very quickly. It's parameterized through this parameters. I will just copy this operation very quickly and create a first pile. The first pile will have a width 0.56 meters, height 0.56, and the thickness also 0.56 meters. Right now, I need to use the master element, which is the wall 1, and using the master point and the insert point, I will put the position of the first pile. So my first point is a number 1, and my second point is a number 4. So it's very easy to use. And right now I will put only X position, which is 0.44 meter. And this is my first pile, which is rated here. In the same way, I will do that for the second one. It's a copy operation. It will be related to the master point or master element 1. Master point will be 2. Insert point will be 3. And X position will be minus 0.44. So you can see it's symmetrical, and we can go on to the other, and it will be the boundary conditions. You can see the software warns you that the structure cannot be calculated because the boundary conditions are missing. So you cannot move forward to another or to the analysis because it's missing. So use the plus button, and here is the portfolio of the supports which can be used, the library. Generally, if you cut the pile here, so the best option is to use the line support, where is also the option to put some stiffnesses, which will be shown in the next example. But today, or this example, we'll be using without the stiffness, and we need to relate it to wall or to the element 2. So master will be W2. We can turn it off, or we need to turn it off, because right now, like a default, is that the boundary condition is has some non-linearity. It means it's not acting in the tangent. So if you click on that, right now it's working in the tangent and in the compression also. And this part will be, the degrees of freedom will be released here. Yeah, so it's acting only in the Z direction. We can copy this operation and put it to the element 3. Oh, okay. But we need to ensure that this X degrees of freedom will be fixed here. So right now it's stable, and right now we'll prepare also the anchors, how to specify the anchors. In the presentations you've shown that there is some equivalent diameter, but what feature used for definition of the anchor? We have some special feature, which is the hanging load. In the hanging load, you can select the shape. The shape will be some lifting stud. The L1 will be 50 millimeters. It will be related to the edge number 3, and the diameter will be 58 millimeters. So the anchorage type, how I mentioned, is a perfect bond, because we consider that these anchors are tied up with the reinforcements which will be modeled like the next step. And the L2 is 0.75. Right now we need to like assign the position of the anchor. The position from the anchor will be measured from the end, and the distance will be 0.8 meters. This is the first anchor, which is here. I will copy this anchor again and put there the X position 1.15. Yeah, so we have specified geometry. That's all for geometry, and we can move on to the loads. In the loads, the first load case is automatically generated. So we will create the free load cases and the free combinations. There will be one load case for ultimate limit state, second one for service orbital limit state characteristic, the third one service orbital limit state quasi-permanent. So at first I will put here or type here the name. It's ultimate limit state, and we will jump into the load impulses. Using this plus button, you can see what like load we can use for design. It will be point load, line load, or surface load. We'll be using this point load. The point load for the first anchor will be 563 and will be related to the transmitting device HG1. So it means this is this anchor. I will change the perspective, and here you can see the force, which is tensile. I will just copy this operation and put here the force to the second anchor, which is 263, and the transfer devices will be HG2. It's here. The load weight, you can put here 1 to has a same scale, and the next step is putting the triangle load as the concrete under compression here. Yeah, this part will be under compression, so we will specify here this triangle load. How to do that? You will use this plus button and using the line load. The line load, if you put 2 numbers here, you will create some shape of the line load. So I would like to have a triangle. So on the one side there will be 0, and the other side there will be the my desired value. So the value is minus 9,300. can see it right now. It's uniform. If I put here 0, here is a 0, here is my value, and I don't want to have it through the all edge, but only the part of the edge will be used. So the X position is 0.8 and the length is 0.64. So you can see I specified very quickly this, and right now we need to put there some shear force, because there have been some shear force. We need to consider it there. How to do that? We'll create another point load. The load will be 125. It will be in the global X direction, and it will be related to the, because this element cannot transfer the shear force. You have to do it in a different way. The different way is that you will select the effective radius. I will explain later, and it will be related to the edge. My edge, you can see, is 1, 2, 3, 4. So I will select the edge number 3. It will be measured from the end, and the distance will have a same position as the first anchor. So it means in this effective radius will be created some constraints, and these point forces will be redistributed over this radius, so over this area. Yeah, to this concrete part will be redistributed this point force. So this is very helpful. I will just copy this operation and put here 1.15 to equally redistribute it to the second anchor. So it was the first load case, which is ultimate limit state. In the same way, we will specify another load case, which is service arbiter limit state characteristic. We can only copy this operation, put here SLS bar like characteristic, go to the load impulses, and only rewrite some values. So the first one is 309 kilonewton. The second one is 163. These are vertical forces in the anchors. The value for load here will be minus 9,119. Don't forget a 0 here. And the shear force will be 100 kilonewton. It's 100, so not 10, 100 and 100 again. So it's the same. And we will copy this operation again and put here the last combination, which is quasi permanent. And so it's very important to specify it, because according to that will be perform the code check. Load impulses, the first point load is the tensile force in the anchor, will be 206 kilonewton. The second one will be 102 kilonewton. The force from the concrete compression is generally minus 7,134. 134 and 0. Don't forget the 0. Yeah. And the shear force will be 80 and 80, equally redistributed to the both anchors. Right now I will jump in here, turn off these load cases, and create 3 combinations, because based on the combinations you will assign to what code check it will be related. So it means I will go through this pen and create this matrix. The first one, the C1, is a combination for ultimate limit state. So I can put here 0 and the 0. The second one is for characteristic. So it means that here will be 0 for the ultimate limit state and service arbiter limit state quasi-permanent. And the last one will be quasi-permanent. So you have to create this diagonal matrix like here, because our design values confirm that it's automatically split it. And that's it from the point of view of the loads, and you can move on to reinforcement design. In the reinforcement design, generally we have 2 options which will help you to design the reinforcement if you don't know how to reinforce it. The first one is a linear analysis. It's very fast procedure, linear analysis of the principal stress and the principal strain, where you can scale it. but generally more visual is topology optimization, which will show you some tensile areas in the compression field. It will remind you something like a Strut&Tie, but generally it's not a Strut&Tie. But it will show you where are the tensile areas and where is the best way for putting the reinforcement. So this is very helpful for the details where you don't know how to reinforce it. Generally, this is the standard. Pile cap is a standard D region, so you know how to do that. But let's imagine that you have something which is non-standard. So let's go on to the reinforcement design, and I will put here the reinforcement. So it will be a very quick procedure because we have we will select the reinforcement type. I will select the group of the bars and start with the reinforcement of the first pile. If you turn off the topology optimization and switch to the 3D rendering, you will see the real reinforcement, how it looks, how many rebars is there. Yeah, so this is only for your imagination, how many rebars is there. So there will be one rebar, the diameter will be 16 and 4 rebars in a layer, but I need to relate it to the wall 2, and the number is 4. I know that my rebars are going through this area down to the pile, so I will use this anchorage shape, so it means it's continuously going down, and I would like to elongate it about 750 millimeters to the pile cap. So here is the option. You will put here 750. You can see it's increased. I will just copy this operation, relate the number to the edge, and only switch the orientation, like this. I will just copy this group of bars. Right now we will do so many copies because the reinforcement is the same for the pile or the entity 3, the element 3. If you select the group of bars 2, you can only copy that, switch the wall 3, and it's like this. Right now we will create the stirrups. This is very important because for walls element like this you cannot very easily put the stirrups, but I will show you what constraints you should use to the behavior was the same as for stirrup. Here is a plus button. I will create a new group of bars which will be related to the wall or the element 2. There will be the edge number 1. So it will create something like this. I would like to have it the diameter 8. There will be 2 bars in a layer, but I would like to elongate it or do more numbers of the layers. So there will be 7 number of the layers after 200 millimeters. And the anchorage shape, which will help you to define the stirrups, is this perfect bond. So it represents stirrups in the model like this. So this is the constraint. In the same way, you can copy this operation and relate it, the stirrups, to the wall 3. And it's remaining the reinforcement of the pile cap itself. We'll create the new group of bars. There will be 1 number of the layers, the diameter 14, 5 bars in the layer, and it will be related to the wall number 1. The shape at the end and at the beginning will be standard hook. And yeah, that's it. Right now we will create more layers. Just copy this operation and start from DH number 3. I will let it straight, and there will be 5 layers after 200 millimeters. You can see it's very highly reinforced, very quickly reinforced, and we can copy this operation again and create the stirrups in the pile cap. So how to do that? I know that there will be 12 stirrups after 250 millimeters. It will be related to DH number 4, and the constraints at the beginning and at the end has to be this one, this perfect bond, which represents the stirrups. And I would like to have there like a 6 latched stirrups. So it means there will be 6. The diameter will be 8, and there will be 6 numbers or bars in the layer. You can see it's reinforced. It's here. You can see it, and that's it. I will save it very quickly, and we can move on to the calculation. Generally, the analysis is very fast. Yeah, but generally, I forgot to shift a little bit this stirrup. Sorry, because there will be different cover. I will just click on the entity. It will highlight it. It's highlighted here, and the cover will be 20. And in the same for the second pile. So value 20 is shifted, and right now we can proceed to check. We will we'll talk about the presentation of the results. How I mentioned at first is calculating. It's a nonlinear analysis, material nonlinear analysis. There are some uniaxial law for concrete and also for rebars. Yeah, you can see the utilization. What is very important on the left side, the ultimate limit state and the serviceability limit state, everywhere are green ticks. It means it's passes. And in the ultimate limit state, the limit condition was the strength of the reinforcement, and in the serviceability limit state, it was a stress limitation code check, 77%. So where to display the reactions? If you click here, generally you can see that this part is under tension. Here is the under compression. It's a line support, so you can read out the value and the equilibrium being developed. So everything is okay. We can move on to the strength and check the stress in the concrete. If you check the stress in the concrete and turn off the reinforcement, turn on the mesh, you can see that the maximum spot is here, 13.9 megapascals. Of course, if you would like to see another results, if you go closer to the element, click on the element, you will see the stress under compression. This is the principal stress in the concrete. Let's say check the results in the reinforcement. You can display here in the ribbon the stress. The maximum stress is here, 344. But if you would like to see, let's say, the stress in the anchor, you will click here and check the stress in the anchor. It's also possible to read out the value everywhere you want. You can see that we consider the rebars under compression and in the tension. This is the element which ensure that. Anchorage, generally this anchorage code check, there is a rigidly plastic diagram, so you can see the anchorage length. It's it's fully anchored, and you can also display the forces in the anchor. You can also display the bond stress in the all rebars, and also display the forces in every rebar you want. You can sort it out here in the table. So it's possible. We will like going to the stress limitations. It's a serviceability limit state where you can display the stresses here, where the maximum stress is minus 2.5, 10.5 megapascals, and also the reinforcement rebars. There is 80% of the yield stress or characteristic yield stress has to be entered here, so it's proved that it's okay, 236 megapascal. Cracks. Generally, where are the maximal cracks? You can see the redistribution of the stresses and the propagation of the stresses. You can see the crack width and the direction. So it's very important to see how it's behave and where is the maximal crack. It's here, it's not here. You can see it's lower value. And the deflections. Deflections, you can check the deformed shape. The maximal deformation is minus 1.3 millimeters. These are the non-linear deflections, of course. So these are the results, and generally this part I will end it up and we'll continue with another part which will be dedicated to with the pile cap with the concrete column. So okay, I will close it and just run another project. We will not model the model from the scratch. I will show you only the highlights which need to be like ensured, and you should pay attention on this part to do the analysis correctly. I will jump to the presentation. I hope you will see my whole screen, and we'll be starting with the pile cap with the concrete column. The model, which you can see here, it's very robust. There is very massive, a lot of concrete is there, big piles, and the concrete column is rectangular shape, 1 meter width, 300 millimeters thickness. The concrete will be the same as from the previous example, C30/37. Grade of the reinforcement rebars will be B500B. This is the inputs. In the first stage, we need to create this equivalent section from the pile, from the circular to the rectangular. So the same equation as in the previous example. But what is different are the stiffnesses on the supports. Generally, the stiffness of the supports like changing the results in the reinforcement in the concrete. So if we were coming out from the real project, what you can see here, and we had also the global model in the FEA. So we knew the reactions, we knew the settlement for characteristic combination, and from that you can calculate like a point spring, which the value is here, and based on the equivalent width, you can calculate the line support or line spring support, which will be used here for definition in the Z direction stiffnesses and create the springs there. So this is the first assumptions, which is what is used in the next example, and the next part which was used is the definition of the load, because generally if you are using FEA, the whole model is created from the members. So you have a members internal forces, you don't have a like a 2D forces, you have a 1D forces. So how to put it to the detail? You can see I have highlighted the normal force, shear force, and the bending moment in the one direction in the plane. To, let's say, fulfill the criteria for plane stress, the other forces should be minor. So it's wallet. You can see this torsion moment, bending moment in the out of plane moments are very low, very low. So this is suitable for detail app. The dominant forces are in the plane. And how to put there the internal forces? The internal forces, how I mentioned, the column has a 1 meter width. So the normal force divided by 1 meter, you can put here the normal force. The shear force will be same, 166.51, like a shear force. And how to create a bending moment? Bending moment is generally you have two forces which has a different orientation, and you need to create from this bending moment this type of the load with for this moment is the intensity for 1 meter 810 kilonewton per meter. So you can calculate it based on stresses or very simple from the really easy equation, and you will get this shape. How to do that in the detail. But before I will jump to the application, I would like to mention the topology optimization. You can see that here is a completely different topology optimization than in the previous example, because there was a marginal, like a bending. Here is a marginal compression force. It's fully, there's a big compression force, and the bending moment is really low. So according to the assumptions in the bottom part of the pile, there will appear some tension. You should put there some another reinforcement rebars, but also in the pile, you can see in the bottom, there are some tensile forces which should be captured by the reinforcement, some stirrups. So you will see that on the example, and we will also interpret some results, how it behaves. So let's go on to the application. I have prepared a model here. It's not necessary to model it from the scratch, but mention how I mentioned important part. So the start will be the same. You will create free walls, but what is very important is the line supports. If you create a line support like one from the type of the support, this is the only condition where you can put the stiffness, and the stiffness in the z direction is 350 meganewton per meter square, will be related to the one and the second support. If I will move on to the loads, I have created samely the free load cases. If I check the load case for ultimate limit state, you will go here, and here is the normal force, minus 5,640. The shear force is 166 in the global x direction. I can just switch the scale, and you can see it's very easily to put it. And how to create this bending moment, this is the crucial bending moment created with string with the 2 points, where the differentiation is only in the sign. So here is the start, here is the end. So the first value will be minus 810, and the second value is 810, but with the plus sign. You will create a bending moment. And totally, if you create a combination, you can see it's automatically summit, and the shape looks like this. Yeah. So this is the shape of the normal force which is acting on the pile cap. The combination rule being done exactly as in the previous example. If I click on the pen, you can see the matrix. Here is the ultimate limit state, characteristic, quasi-permanent combination. If I will move on to the reinforcement design, here are some standard reinforcement. If you click on the 3D rendering, you will see how the reinforcement looks like. The same principle as in the previous example. So 8 entities, and I can move on to the check, because I would like to show you how the results looks like. So in the summary, you can see that here is a very big portion of the concrete utilization. That's approximately or almost 100%. So the strength of the concrete is a crucial condition right now. If I check the reaction and check only the vertical, you can see that it's true. It's really compressed. There is a big portion of the normal force. Let's check the strength tab. In the strength tab, if I switch to the concrete, so you will see, and turn off the reinforcement, draw the mesh, you can see the discretization. The maximal values generally are related here. Of course, there is the support, so there is some resolution of the stresses. But what is very important, this part is really under compression. If I check the reinforcement, we can, it's been seen that at this part is some tensile forces, but also here. But the dominant tensile forces are related to the bottom edge of the pile. If I check the value, sort it out, sorry. So the maximum value is here, it's in the pile, and the second maximum value is in the bottom of the pile. So these are our assumptions has been fulfilled. It works pretty well, and we can move on to the anchorage. In the anchorage, you also see the 99.8% of the utilization, where the maximum utilization is here. So here is a really big transfer strain or transfer stresses, which should be captured by the reinforcement, which is there. I can also display the force in the rebars itself. The marginal is here, of course. And we are moving to the stress limitation. In the stress limitations, there is a stress limitation condition for concrete and also for rebars, and the maximal spot is close to the corner here, 8.1 megapascal, and for the reinforcement rebars, it's here 369. So we are very close to the limit. And the cracks. The dominant cracks are presenting here. You can see the stress redistribution of the cracks, also the maximum value. So according to the assumption, it behaves pretty well. Deflection, if you check the deformed shape, you can see there is completely 9.9 millimeters, but you need to keep in mind that there are spring supports which ensure this big deformation. So I am coming till the end. I will create a report which can be reported or exported to the Word and the PDF. You can also customize your protocol, because you can turn on and turn off some loads, topology optimization, reinforcement, some enhanced results, bill of the material. But what is very important, you can see the content, the structure of the protocol. You will get the material properties, some geometry, also the loads, the combinations, some scheme of the reinforcement, and the depth, the summary overview of the results, and the very detailed and enhanced presentation of the results for all ultimate limit state and the serviceability limit state results. Yes, the bill of the material, some explanation, and yeah, that's it from my side. I'm passing the word to Petya. So you can take it, Petya. So yeah, we can see that.
Okay, so let's summarize a little bit what you just learned about detail application, why it's actually helpful. So first thing, the time. You can design the pile cap much faster. The conservative methods are time consuming, so yeah, that's one of the benefits. The second one is the material. You can pick material with the all parameters, and you have all code checks, even for service stability, like cracks and deformations. So that's what the application offer. And before we will continue to the question part, I would like you to vote one more time. And the question is, what is the biggest benefit by using the detail application, like for you? So please, again, you can pick one answer. You have again just few seconds, and then I will share results with you. You could see there is more benefit, but what's really important for you. Okay, we have last 5 seconds, and then I will close the poll. Okay, let's see what we got. So it's like half and half, precision of the results and optimization. So the time and the code checks. That's something what we expect, and we are glad that you see the same benefits as we do. And now let's move to the next part when Lucas will answer some of your questions. There was one that keeps repeating, and it's about the piles. So it's possible to model the circular piles, and it's the approach appropriate because sometimes you, or not sometimes, but the reinforcement, it's a different like place or different location, or the stress redistribution is a little bit different for the piles when it's circular or when it's square. So can you
Yeah,
talk about it a little bit?
yeah, sure. I can answer. There is the option to create the palcaps with the circular section, but it's very complicated. Generally, just keep in mind that there are some assumptions of the plane of the stress, plane stress task. So it means it's only in the plane. Generally, the modeling of the circular sections this is not so supported. You need to create some workaround there, but there is the option. But this is the reason why I created the circular section. I know your perspective that there is a different reinforcement like layout in the circular section, but if you will create the circular section there, so of course you can put there some different reinforcement layout, but it's let's say more complicated and less effective for the modeling and the speed progress and working in the application. So this is my answer for that.
Thank you. And then another question that it's like more times. Can this method in IDEA also be used for pile skips with supported by multiple piles in both the short and the long direction of the pile cap?
Yeah, generally you can put there so many piles you want, but it has to be in the plane. It can be longer or shorter, whatever, but you cannot create like a pile cap in the space or the 3D pile caps that there will be some, let's say, triangle of the piles, and it will be behaves like a 3D model, because there is a stress in the three directions, and in our model we consider the stress in the both direction. The third dimensions is only the thickness, yeah, so there is no stresses over the thickness. And this is what I'm mentioning. This is the assumption of the plane stress model you need to keep in mind before you start the analysis and the calculation of the model like this.
Thank you. We are kind of running out of the time, but all the questions will be answered after after the webinar, so no worries, and we will move a little bit. So after the webinar, you will
Petty,
receive.
you have their poll. There is the poll is still appearing there,
Ah,
so you have to close
sorry.
it. Yeah, no worries. Okay. Yeah, right now we can see your presentation.
Okay. So after the webinar, you will receive a short survey. Please give us a feedback as we want to improve and get better. Also, if you want to rewatch or share the webinar, you will find a recording in Support Center or our YouTube channel. If you are completely new, you can download the trial version at our website ideastatica.com, or you can go to the Support Center if you need some help. You will find tutorials, other webinars, articles there. So use it when you are a little bit lost. Okay. I would like to highlight from our support center the new campus. It's a e-learning course. We already had 3 topics for steel, and recently, a few days ago, we launched new course for concrete. I will show you where to find it. When you come to the support and learning, it's in the drop-down menu, it's learning and certification. You can just pick the course and it's free. So you can come back, you can learn from the scratch, or you can just jump to the section you need. You can go one by one to learn principles and how to work with the detailed application. At the end, you can pass the quiz and get the certificate. So it's something what's new. And back to the presentation. Last but not least, next webinars are coming. You can already put in your calendars. First one is at the end of the March, prepared by US Office. Its topic, the structural loads in connection design. And the next one at the beginning of the April, our regular series, Connection Wednesday. That's it from my side. Thank you very much for your time, and I hope you learned something new and useful.
Yeah, thank you, and see you on the next webinar. Bye bye.
Bye.